Okay, now we're going to spend a little more time with Newton's second law. Now, our objectives are to explain the relationship between acceleration, force, and mass, and then apply Newton's second law to a variety of problems, differentiate between mass and weight, and understand static equilibrium, and introduce you to dynamic equilibrium. Now, Newton's second law of equation is actually a mathematical equation. The sum of the forces equal m times a. Now, the way Newton originally wrote it, he said the acceleration of an object is directly proportional to the net force applied and inversely proportional to the mass. So in other words, Newton actually wrote it this way. He said a is equal to F divided by m. But the key thing to understand that was net force. Now, it's a lot easier, in my opinion, to write it as a flat equation and move the m to the other side, that the net force is equal m times a, and that is most of the times the way you see it. But again, this is the way that Newton originally understood it. He said if you apply a force to an object, that object is going to gain an acceleration. And then he said if you apply a force to a larger object, the acceleration is going to go down. And that's the way he kind of reasoned his way through it. Now, comparing Newton's first law and second law, Newton's first law involves things staying the way they were, either at rest or at a constant velocity in a straight line. So the sum of the forces in that case would be equal to 0. There is no leftover net force. With Newton's second law, you're going to now talk about things accelerating because there is a leftover force. There is a net force. Remember, leftover force, net force, and unbalanced force are all the same thing. Now, to apply Newton's second law, first thing we want to do is draw a free body diagram. We'll do those in class. Then write expressions for net forces in the x and y directions, because I can separate it. Fx is equal to m times a in the x direction, and Fy is equal to m times a in the y direction. Now, right now, we're really going to talk about objects moving in either the x direction or the y direction, and then you solve the equations. Now, so we have a 25 Newton force east and a 25 Newton force west acting concurrently on a 5 kilogram box. What is the acceleration of the box? We have to assume it's on a frictionless surface since we didn't measure that. So first of all, let's draw a little picture of what's going on. There's our box. I'm going to say north is that way, so therefore that defines all my other directions. Okay, I have 25 newtons pointing to the east. I have 25 newtons pointing to the west. Obviously, it can only accelerate in that direction if we assume it's sitting on a flat surface. So therefore, when I go to solve it, I say the sum of the forces equal m times a. Well, what's the sum of the forces? 25 minus 25 is 0. 0 is equal to 5 kilograms times a, so therefore a is 0. And again, there is no acceleration. Those forces balance each other out. You can be moving and not accelerating. A 0.15 kilogram baseball moving at 20 meters per second is stopped by a player in 0.10 seconds. What is the average force acting on the ball? So if I draw a free body diagram of the ball, I'm going to have the ball there. I'm going to have Fg acting down. And I'm going to have a force that goes in this direction applied by the catcher. So that, and it's going to go down. We will consider this to only be moving in the x direction, even though it's going to have some y component. But since we haven't talked about projectiles yet, the only force we need to worry about is that one. So I'm now going to say sum of the forces in the x direction are equal to m times a in the x direction. So now, I don't know a. So what I'm going to have to do now is treat it like a kinematics problem and solve for a. So when I do that, might actually help to, maybe I can't. Okay, now I treat it like a kinematics problem. VI is 20, VF is 0, and that's meters per second. T is 0.10 seconds. And I want to calculate A. Well, since A is equal to delta V over T, I'm going to have 0 minus 20. It's going to be negative 20 meters per second divided by 0.10 seconds is 200 meters per second squared. And that's a negative value. Now we come up here and plug and chug. The sum of the forces in the x direction are going to equal 0.15 kg times 200 meters per second squared. Sorry, that's getting kind of ugly looking. 0.15 times 200 is 30 kilograms times meters divided by second squared. And again, that is a Newton. Go back through that, rewind it if you need to for that. Okay, two forces F1 and F2 are applied to a block on a frictionless horizontal surface as shown. If the acceleration of the blocks is 2 meters per second squared, what is the mass of the block? Well, we're obviously dealing with a force, a mass, and an acceleration, and we're in the x direction is equal to m times a in the x direction. And again, our unknown is mass. So what do we have? Just for fun, I'm going to say that this direction is positive. Again, you choose positive or negative, so you can do either one. The sum of the forces in the x direction, well, it's negative 10 newtons. 2 minus 12. And again, because I chose this as my positive value, it's in a negative direction. That is equal to m, which I don't know, divided by a. Now, we have to assume that it's moving in the left direction, because if you look at those two forces, based on what we see, it's going to accelerate to the left direction. So therefore, the acceleration is also negative. So negative 2 meters per second squared. So then when I solve, I divide both sides by negative 2. I get m is equal to 10 divided by 2, which is 5. And it's kilograms times meters divided by second squared, divided by meters per second squared, which is kilograms. It's a 5 kilogram box. Let's try another. A 25 Newton force acts north and a 35 Newton force acts south concurrently on 15 kilogram object resting on a frictionless surface. What is the magnitude of A? So we're essentially going to have an object sliding. And we have 25 newtons going one way and 35 newtons going the other way, resting on a frictionless surface. I'm going to say north is this way. Again, I can choose north. I'm going to assume that the tabletop is that way. So now, when I sit there and look at it, I'm going to say the sum of the forces now, it's constrained to move only in the x direction. The sum of the forces in the x direction equals 0. The sum of the forces in the x direction, well, if this is positive, if this is north, I have 25 newtons going this way, and I have 35 going this way. Notice how I drew my 35 Newton vector longer than my 25 Newton vector. So what I have is negative 10 newtons. That's based on my convention that that was going to be north. So therefore, if that's north, I'm also going to say that that's positive. So therefore, I have 25 minus 35. That's equal to m times a. Well, it's not 0. I don't know what I wrote that for. Apologize. So therefore, m times a. So m is going to be 15 kg divided by a. If you divide both sides, you're going to get A is equal to 10 divided by 15, which is 0.67. It's negative meters per second squared. Now, why is it negative? It's simply negative because this side wins. And again, that's opposite of the way we called positive. Now, we talked about this briefly already. Weight is the amount of inertia an object has. It only depends upon the mass and nothing else. Weight is the pull of gravity on that mass. And if I go to a place that has a new gravity amount, I'm going to have a new weight. The way we write it traditionally in equations is F little g. F sub g is equal to m times g. I want to get you away from writing WT or the W for weight because W is spoken for, excuse me. Sorry. Now let's do a mass and weight example. What is the weight of a 2 kilogram cat? So I'm looking for Fg. Fg is equal to m times g. Now I don't really need to draw a picture for this. We'll get into drawing pictures later. I have a mass of 2 kilograms. G is 9.8 meters per second squared. 2 times 9.8 is 19.6. And it's kilograms times meters divided by second squared. That's way too hard to write all the time, so let's call that a Newton. Now, static equilibrium. Static equilibrium means something is stationary. Well, or the force is balanced, I guess is probably a better way. It doesn't have to be stationary. It just simply says there's no net force, so therefore the acceleration is 0. Now, we will use a term called the equilibrant. The equilibrant is the force required to bring an object into equilibrium. So if I have some type of net force, it would simply be something that brings it back into equilibrium. And the equilibrant is equal in magnitude but opposite in direction of the net force vector. Now in the diagram you have a 20 Newton force north and a 20 Newton force west act concurrently. What is the additional force needed to bring it into static equilibrium? Key thing to understand is if I have 20 newtons up and 20 newtons to the right, the object's going to move this way. Now the way I calculate how much it's going to move this way is draw one of the vectors over here. So that dotted line is going to be the path at which it follows. So let's figure out the net force. It'd be 20 squared plus 20 squared. So 400 plus 400, the square root of 800. And I forget exactly what that is. It's going to be... Let me get a calculator and try that. So of course this is going to be 28 newtons when you solve it. 20 squared plus 20 squared and then the square root of that, 28 newtons. The equilibrant would be 28 newtons, but pointing that direction, the opposite direction, it was the one that would bring it back to equilibrium. So in other words, essentially you went that way with a force, then went that way with a force. The equilibrant is the one that brings you back into that corner to close the triangle. Now, if I have a 3 Newton force and a 4 Newton force acting on an object, what force could not produce equilibrium with these two forces? Well, the way to look at this is to think about what's the maximum I could have. So if I get an object here, the maximum I could have is if I have 3 newtons this way and 4 newtons this way. The maximum I could have would be 7 newtons. Now, what's the minimum I could have? Well, the minimum I could have, so this is max. The minimum would be if I had 3 this way and 4 this way. Then your minimum is 1 newton. I can really get anything between 1 and 7. That means I can't get 9. More on vectors in the future, but I just want to make sure that we're thinking that way right now. Now, dynamic equilibrium is when you have an acceleration. You're now causing something to move. For example, a rocket that continues firing its rockets in space. There is a net force in this case. It is going to accelerate. So let's take a look at one on the next page. Okay, a reluctant 10-kilogram dog is being pulled towards the vet to get fixed. And let's come up with a force. Let's say we're pulling with a force of 60 newtons. So let's go find a picture of a dog. Let's go do. Okay, now we got a picture of a dog. So what we're going to say is that the person is pulling with a force of 60 newtons. So I have 60 newtons acting this way. There's my dog. If friction is 30 newtons, now friction always opposes motion, so I'm going to draw 30 newtons this way to represent friction. And right now I'm just going to label it with numbers. As we do more free body diagrams, we'll get to other things, but we'll do that right now. I want to know the acceleration of the dog, so I'm going to say the sum of the forces in the x direction are equal to m times a. Well, let's go ahead and say the way he's being pulled is positive. Now, I'm winning the battle. I know that because 60 and 30. Now, I'm going to now say 60 minus 30 newtons. So 60n minus 30n is equal to 10 kg times A. 60 minus 30 is 30 newtons, is equal to 10 kg times A. A is 30 divided by 10, which is 3. Newton, which is a kilogram, times meters divided by seconds squared divided by kilograms, leaves you with meters per second squared. So the dog is going to accelerate towards the vet's office to get fixed. We'll do a whole bunch more of these in class. You need to get comfortable with these. Okay, have a good day.